Hey, Joe, what's the outlet pressure to the superheater?
Let's see. It's running at 850 pounds.
Hey, thanks.
All right.
Quite a night last night.
Well, you guys go bowling?
Oh, yeah, did pretty well. Hey, I hear the boys in the operating room had quite a control upset last night with boiler number 2.
Oh, yeah. Pressure got so high it lifted the safety valves. Yeah, I could hear them clear over at the instrument shop.
Just what do we mean when we use the term pressure? Imagine a tank which contains a pressurized fluid. This air receiver, for example. A compressor pumps air into this tank for use in operating instruments, controls, and other pneumatic devices. Let's say the air pressure inside the receiver is 100 pounds per square inch. What does that mean? Pressure is defined as the amount of force applied by a pressurized fluid on each unit area of its container. The compressed air in the tank exerts an equal force in all directions. If the pressure in the tank is 100 pounds per square inch, that means the air is exerting a force of 100 pounds on each square inch of the tank's surface. Another way to understand the relationship between pressure and force is to look at the force, and therefore pressure, exerted by a quantity of liquid on the bottom of its container. Imagine that this container is a 12-inch cube completely filled with water, so we have exactly 1 cubic foot of water. The bottom of the container has an area of 12 times 12, or 144 square inches, and we know that 1 cubic foot of water weighs 62.4 pounds. The total force applied to the bottom of the container is 62.4 pounds. We said pressure is force per unit area. How much pressure is applied by the column of water over each square inch of the container's bottom? We can determine the pressure applied to 1 square inch by dividing the total weight, or force of the water, 62.4 pounds, by the surface area, 144 square inches. Therefore, the pressure applied to each square inch of the container bottom is 0.433 pounds. This pressure caused by a standing column of liquid is called hydrostatic head. Hydrostatic head varies with the height of a liquid. It also varies with the liquid's mass, or density. We'll learn more about density in a few minutes. So, pressure is equal to force divided by area. We can see from the pressure formula that changes in either force or area will cause pressure to change. For example, if area increases, pressure decreases, and if force increases, pressure increases. By substituting the most common units for force and area in the pressure formula, we can determine the most common unit of pressure. If pressure is equal to force in pounds divided by area in square inches, then the unit of pressure will be pounds per square inch. This is usually abbreviated PSI. As you know, the Earth's atmosphere exerts a pressure on the face of the Earth and everything on it. This pressure is referred to as atmospheric pressure. Although it varies with weather conditions and altitude, atmospheric pressure is usually about 14.7 psi. Atmospheric pressure must be considered and allowed for in instrumentation and control systems, which measure pressure in plant systems. Most industrial pressure gauges and instruments indicate what's called gauge pressure. Gauge pressure is actually the difference between atmospheric pressure and the system pressure that's being measured. Gauge pressure is usually expressed in pounds per square inch gauge, or PSIG. Some pressure instruments, however, measure and indicate absolute pressure. Absolute pressure is measured without regard to atmospheric pressure. That means that the complete absence of any pressure or a perfect vacuum would result in a reading of 0 on an absolute pressure instrument. A common unit of absolute pressure is pounds per square inch absolute, or PSIA. Here we see 2 pressure gauges connected to the same process system. Do you think both gauges are reading accurately? If you said yes, you're correct. If both gauges are indicating the same pressure, the difference in readings between a pressure gauge indicating gauge pressure and one indicating absolute pressure should be equal to the atmospheric pressure, about 14.7 psi. Another way to measure pressure is to relate it to the hydrostatic head of a column of liquid. That's the principle at work in a manometer, such as this one. This manometer is a U-shaped tube containing a liquid. A graduated scale is used to indicate the height of the liquid in the tube. In this example, for demonstration purposes, the liquid used in the manometer is colored water. This well-type manometer has a single tube. As the pressure on the liquid changes, it causes the liquid level to change until the hydrostatic head of the liquid in the manometer equals the pressure being applied. The pressure value is read in inches of liquid. A change in pressure of 1 psi is equal to a change of 27.7 inches of water. Manometers like this one are sometimes found in industrial applications. In most cases, however, gauges or other pressure instruments are used, but they can be calibrated so that inches of liquid indicates the scale value. This gauge, for example, indicates pressure in inches of water. Here, two manometers indicate 100 inches of water, but the liquid heights are different. Remember, we said that hydrostatic head varied with the mass or density of the liquid as well as its height. The reason these two manometers don't have the same level is that they're using two different liquids, water and mercury. Since mercury is heavier than water, it doesn't rise as high as water when the same pressure is being measured. The term used to compare the mass of liquids is density. Density is calculated by using the formula density equals mass divided by volume. Typical units of density include pounds per cubic foot, pounds per cubic inch, and ounces per cubic inch. Another term that you're probably familiar with is specific gravity. One use for specific gravity is checking a battery's state of charge. The specific gravity of a battery's electrolyte is frequently measured as an indication of the battery's charge. Specific gravity is a ratio that compares a fluid's density to the density of water. The formula for specific gravity is specific gravity equals the density of the fluid being considered divided by the density of water. For these purposes, the standard density of water is 62.4 pounds per cubic foot. In working with the instrumentation and control systems in your plant, you may sometimes need to convert between different pressure units. You may also need to determine and compare the densities of different fluids. Your workbook contains a number of useful formulas for these calculations, as well as conversion tables.
What's the level in the number 6 makeup tank?
How long will it take to fill a storage tank if we maintain this flow?
How many gallons do we have in the batch tank?
If we keep going at this rate, will we empty the feed tank before the end of the shift?
To find the answer to any of these questions, we would have to know the volume or level of the liquid in a container. As we're about to see, volume and level are directly related quantities, but they are not exactly the same thing.
Paul, how's it going?
Hey, Mike, how you doing?
I'm doing pretty good. Look, I got a question for you.
Yeah.
Now, the level in the number 6 feeder tank is 13.5 feet. Now, if I wanted to know how many gallons were in the tank, how would I calculate?
You'd have to calculate the volume in the tank by taking the formula for the volume of a cylinder and substituting the diameter of the feed tank and the height of the fluid. Then you'd solve the formula and convert the answer to gallons. It's pretty easy to do. Here, let me show you. The formula for volume is...
The term volume refers to the amount of space occupied by an object or fluid, in this case, the space occupied by the fluid in a tank. Volume can also be used to express the capacity of a container. For example, if we know this tank's capacity, and we know that it's half full, we can calculate the amount of liquid it contains. First, we have to know its total volume or capacity. The volume of a container can be calculated from its dimensions. If this rectangular container is 2 feet wide, 2 feet high, and 3 feet long, we can find its volume by multiplying these values together. The formula for the volume of a rectangular container is length times width times height. In this example, 3 times 2 times 2 is 12. So the total volume or capacity of this tank is 12 cubic feet. If the tank is half full, it contains 1/2 of 12 or 6 cubic feet of liquid. Now, how does volume compare with level? Level is defined as the location of the interface between two phases of a substance. For example, the interface between the steam and water in this boiler steam drum. Or the location of the interface between two substances, such as the liquid and air in this tank. The level in a tank or vessel can be measured with a simple device, such as this sight glass. A sight glass is a transparent tube. The bottom of the tube is connected to a point on the tank which is below the liquid level, while the top of the tube is connected above the liquid level. So, if the tank is vented to atmosphere like this one, the top of the tube is also vented to atmosphere. In this case, two overlapping sight glasses are installed on a tank. Since liquids seek their own level, the level in the sight glass tubes will be the same as the level inside the tank and can be directly observed. Sight glasses are accurate, simple, and reliable devices, but they also have limitations. They provide only a local indication of level, and they can present a hazard if broken. Instrumentation systems that measure and indicate level are frequently provided in addition to or instead of sight glasses. They enable accurate remote level indication and control. There are many ways that instrumentation systems can measure the level in a tank or vessel. One method makes use of a principle we discussed in the segment on pressure, that the hydrostatic head of a column of liquid, in this case the level in a tank, is proportional to its height. You'll recall from our earlier discussions that there is a direct relationship between the height of a fluid and the pressure it exerts on the bottom of its container. This tank is partially filled with fluid. A transmitter senses pressure at the bottom of the tank and produces a signal proportional to the pressure. The instrumentation system then compensates for the density of the fluid and generates a signal proportional to the tank level. Such a system would not be accurate on a closed tank which is pressurized. Now, the pressure at the bottom of the tank is a combination of the hydrostatic head of the liquid in the tank and the vapor or gas pressure on top of the liquid. Pressure on the bottom of the tank does not correctly indicate the level in the tank. In this case, a differential pressure transmitter senses pressure below the liquid level and above the liquid level. The pressure measured at the top of the tank cancels the vapor or gas pressure portion of the pressure measured at the bottom of the tank. The difference between the two measured pressures, or differential pressure, is the hydrostatic head, which is proportional to level. When pressurized vessels contain steam or some other vapor which could condense in the upper low-pressure reference leg, the level indication would again be extremely inaccurate. We would now be sensing the hydrostatic head of the condensed vapor as well as the static vapor pressure on the reference leg. When condensation could be a problem, the upper sensing line is intentionally filled with liquid. Now the differential pressure determined by the instruments is the difference between the hydrostatic head of the filled column, the reference leg, and the hydrostatic head of the liquid in the vessel. After compensation for the known height of the reference leg and the densities of both fluids, this differential pressure signal is again indicative of only the hydrostatic head or level of the liquid in the vessel. No matter how it's measured, level is a volumetric measurement. It can be used to directly determine the volume of fluid in a container. In fact, many level indicators are calibrated in units of volume. If we needed to know the mass of fluid in a container, we would have to multiply the fluid's volume by its density, or an instrumentation system could measure the fluid's weight. We have seen only two of the many ways that level can be measured. As you continue your study of instrumentation and control systems, and as you become familiar with the systems in your plant, you'll learn about other level measurement methods. Your workbook contains some additional information on level measurement, some formulas for calculating the volume of different shaped containers, and review questions to allow you to check your understanding of these topics. As you know, the molecules of all substances, even solids, are constantly in motion. Temperature can be defined as the measure of the internal molecular activity of a substance. When heat is added to a substance, molecular activity increases. This is seen as an increase in the temperature of the substance. Temperature can be measured and indicated on several different scales. In most instrumentation and control systems, you'll find that temperature is displayed on the Fahrenheit or the Celsius scale. There are several methods of measuring temperature. The method for a particular system is determined by the range of temperature that needs to be measured and by the range of the temperature sensor. The sensor chosen must also be compatible with the other components of the instrumentation system. Industrial bimetallic thermometers are mechanical devices. Most work on the principle that when their temperature is changed, different metals expand or contract at different rates. Here we see a thermometer sensing element made of two dissimilar metals bonded together. When the element is heated, the two metals expand. But if one of the metals, the lower one here, expands more than the other, this causes the element to bend. In an industrial thermometer, one end of the sensing element is anchored to the thermometer housing, while the other is attached to a mechanical linkage which positions the instrument's pointer. Industrial thermometers are rugged and inexpensive. Their major limitations are relatively low accuracy and the fact that they provide only a local indication of temperature. In order to have accurate remote indication of temperature, a detector that converts temperature to an equivalent electrical signal may be needed. One type of electrical temperature sensor is a thermocouple. Thermocouples convert temperature to an equivalent millivolt signal, which changes in response to temperature changes. Thermocouples are constructed of two wires made of two different metals. If two dissimilar homogeneous metal wires are joined at each end to form two junctions, and a temperature gradient exists between the junctions, a millivoltage is produced. A thermocouple's wires are joined at one point where temperature is sensed. This is the measuring junction. The other junction, where the thermocouple is connected to the instrumentation system, is maintained at a constant temperature. This is called the reference junction. When the measuring junction is heated, a DC millivoltage, proportional to the temperature difference between the two junctions, is generated. This signal represents the temperature being measured. The amount of voltage produced is determined by the type of thermocouple and the materials of construction. Typical thermocouple wire combinations include iron and constantan, copper and constantan, chromel and chromel-alumel, and platinum plus 10% rhodium. Your workbook contains tables which show temperature versus voltage for several thermocouple types. Here we see an installed resistance temperature detector. The appearance of resistance temperature detectors, or RTDs, is similar to thermocouples, but their operating principle is entirely different. An RTD is constructed of metal that varies in resistance in proportion to its temperature. As temperature increases, an RTD's resistance increases. Changes in an RTD's resistance are measured and converted to temperature values. This illustration represents a thermistor-type temperature detector. Thermistors are solid-state devices. Like an RTD, a thermistor's resistance varies with temperature. But unlike an RTD, when a thermistor's temperature is increased, its resistance decreases. When calibrating, troubleshooting, or repairing a temperature loop, you'll have to know the type of detector used and its characteristics in order to understand the operation of the loop. The performance of a temperature loop is affected by the thermal conductivity of the process fluid, the temperature detector, and the heat transfer capabilities of the system components. Thermal conductivity is the ability of a substance to transfer heat. Some substances transfer heat better than others. Here we can see the molecular activity or temperature of this substance is greater on the side exposed to the heat source. If temperature was being measured here, it would be lower than if measured here. The difference is due to the thermal conductivity of the substance. Thermal conductivity affects the accuracy and response time of temperature sensors and must be allowed for when calibrating temperature loops. Thermal conductivity is taken into consideration when determining a temperature sensor's location in a system, as well as its location in a pipe or vessel. Temperature detectors in some process systems are inserted into the piping and exposed directly to the process fluid as shown here. But usually, the sensors must be installed in a thermal well to protect them from the process fluid. Thermal wells separate sensors from process fluids. Among the advantages of thermal wells is that they allow removal of the sensor while the process is in operation. Their primary disadvantage is increased response time. The thermal conductivity of the walls of a thermal well and the substance inside it, typically air or a liquid, reduce the response time of the sensor. Your workbook contains some additional information on the measurement of temperature in industrial processes, the types of detectors, and thermal wells. Flow rate, or simply flow, is defined as the quantity of a fluid which moves through a pipe or channel in a given unit of time. The flow of steam is usually measured in pounds per hour, or where flow is high, you may see steam flow indicated in hundreds or thousands of pounds per hour. Liquid flow is frequently expressed in units of gallons per minute. Gas or air flows are usually measured in cubic feet per minute. These three examples of flow units illustrate the two types of flow measurement. Steam flow in pounds per hour is an example of a mass flow rate. Since we are measuring quantity in pounds, a unit of mass or weight, we are measuring the mass of steam flowing in a unit of time. The other two are both examples of volumetric flow rates. Gallons and cubic feet are both units of volume. So in both these cases, the units indicate that we are measuring the volume of fluid flowing in a unit of time. As with other variables, flow can be measured in many ways. One way that instrumentation systems can determine the fluid flow in a pipe is to measure the pressure drop across a restriction in the flow. Here we see a differential pressure transmitter. The transmitter senses pressure on each side of an orifice plate installed between these flanges. As the fluid flows through the orifice plate, its potential energy in the form of stored pressure is converted to kinetic energy in the form of velocity. As this conversion takes place and velocity increases, pressure decreases. So whenever there is flow through a restriction, the pressure on the downstream side of the restriction will be lower than the pressure on the upstream side. As flow increases, the difference between the two pressures, or the pressure drop across the restriction, also increases. This pressure drop, usually referred to as differential pressure, is mathematically related to flow. Flow is directly proportional to the square root of the pressure drop across a fixed restriction. So, if an instrumentation system senses pressure upstream of this flow restriction and also downstream of the flow restriction, and then calculates the pressure drop, the differential pressure can be converted to a signal representing flow after compensating for the pressure and density of the fluid. Flow rate can also be determined by measuring the differential pressure caused by flow through a venturi tube. Since there are no sharp edges in a venturi tube, they are especially well suited for systems containing dirty fluids or slurries. Flow nozzles such as this one also produce a differential pressure that can be converted to flow measurement. They are well suited for steam flow and other high-velocity fluid flows where erosion could be a problem. The flow of fluid through a curved path, such as a piping elbow, also generates a differential pressure proportional to flow. An elbow tap flow meter is based on the principle that the acceleration of the fluid around the curved path creates a centrifugal force causing the pressure on the outside of the curve to be greater than the pressure on the inside of the curve. Flow measurement loops making use of differential pressure measure volumetric flow. If mass flow measurement is needed, the instrument system must also measure fluid pressure and temperature. Here we see a magnetic flow meter. Magnetic flow meters measure volumetric flow. Two coils generate a magnetic field. As a conductive fluid flows through the metering tube, a potential is produced in the fluid. Electrodes projecting through the metering tube's lining sense the induced voltage. Since the magnetic field is constant, the voltage is directly proportional to the fluid's velocity and thus its volumetric flow. This flow meter is called a vortex shedder. It consists of a blunt, flat-faced body called a shedder, a sensor, and a transmitter. As fluid flows past the shedder, it swirls, causing alternating vortices downstream. The sensor measures the frequency of the vortices. This measurement, processed and amplified by the transmitter, is proportional to fluid velocity and flow. Here we see an axial turbine flow meter. In this design, a turbine rotor is placed in the fluid flow path. Fluid passing through the unit causes the rotor to turn with a velocity proportional to the fluid's flow rate. The electrical pulse generated in a pickup coil is proportional to the speed of the rotor, and therefore indicative of fluid flow. We have seen only a few of the many ways that flow is measured in industrial instrumentation and control systems. Your workbook has some additional information about flow and how it is measured. And it contains questions to allow you to check your understanding of these topics. It also contains some examples of other process variables. The information you have learned about pressure, level, temperature, and flow, together with the physical principles behind their measurement, will contribute to your understanding of the processes and systems in your facility. Remember, however, that designs and operating principles differ, so always follow the manufacturer's instructions and your facility's guidelines before working on any process system.